Hello dear colleagues and another welcome to your channel. In this video we are going to continue our tutorial about steel structures and steel materials, properties, etc. You know, uh, this session topic is most important properties of steel. But first of all, I'm gonna introduce you the tension and strain diagram of steel. Let me draw that. The horizontal axis is for strain and the vertical axis is for tension. This is a strain. I just want to draw for most general type of steel, which has this diagram. At first, the shape of diagram is elastic and with a very high elasticity. In this point, steel will yield, and the rest of the diagram has this shape, and in this point area steel will yield, and the yield stress of general steel is 2,400 kilogram divided by square meter of centimeter, or we call it the custom steel that we use in structures, ST37 or S235JR. Get familiar with this name, okay? And when the loading is started, steel has very stiffness, and the shape of the diagram is like so, because there is so much stiffness. And in this point, steel will yield, and we have the decretion of tension, and then we have another one, strain hardening. Let me write that for you. Strain hardening. And this thing will continue until the steel will be ruptured, and tension will be decreased. This is the common diagram for steel. Okay, and in continue, I want you get familiar with the properties, engineering properties of steel, that we use them in civil engineering. The engineering properties of steel. The first thing that I want to introduce you is the modulus of elasticity that we show them with the E. So the first one is modulus of elasticity, that we show that with the E, E is equal to 2 times 10 to the power of 5 megapascal, or approximately 2 times 10 to the power of 6 kilogram divided by square meter of centimeter. The thing that we should be cautious in this thing is that the modulus of elasticity of steel is not dependent on the strength, yield strength of steel. Is not dependent to Fy. But in concrete, this is not so. The modulus of elasticity of concrete is completely dependent to concrete strength. That's really, really important. Another thing that I'm going to introduce you is the yield stress and the ultimate stress. Yield stress and the ultimate stress. For this type of steel that we call it S235JR, that is used more common in creating of structure. S235JR. For this type of steel, we have yield stress of the steel as 2,400 kilogram divided by square meter of centimeter, and the ultimate stress is 3,700 kilogram divided by square meter of centimeter. This is another properties for steel. Sorry. And the third one I want to tell is that let me change my marker. The third one is the Poisson coefficient. What is the Poisson coefficient? This content is used when we have a axial force on a body, steel or concrete and everything else. When we apply an axial load on a circumstance body, on a body, there is lateral pressure too, and because of that axial force, this body will have increase in have increase in volume or mass. So let me repeat that. Due to axial pressure, we have increase in body. We have increase in value of body. We have increase in value of the mass of that body. Okay, we call Poisson coefficient Poisson ratio 2. Okay, for steel, this ratio is 0.3. Let me show that with the shape. For example, this is a mass or a steel, concrete, everything else. We have axial force on this body, and because of this axial force, we have lateral increasing in volume. The size of that body will be increased due to Poisson ratio. Okay, another thing that is the properties of steel is temperature coefficient. Sure. Coefficient that for steel is 12 times 10 to the power of -6, 1 divided by centigrade. The fifth properties of steel is shear modulus of the shear modulus of elasticity, that we show that with G letter. G is equal to E that I have introduced, that with 2 times 10 to the power of 5. E divided by 2 times 1 plus Poisson ratio, that we have Poisson ratio as 0.3, and then the coefficient of shear modulus of elasticity is E divided by 2.6, which is equal to 7.7 times 10 to the power of 4. Is a very, very huge number, and we can write that approximately 7.7 times 10 to the power of 5 kilogram divided by centimeter to the power of 2. These were the most important properties of steel that I wanted you to know that, but I know that you all know it, but just for reminding, I tell that. Okay, let's continue. Now I want to introduce the most important profiles of steel. Let's continue, everybody. The first profile that I want to introduce that is INP. And the second one is IPE. All of them has this shape with different thickness and radius in the with different thickness in a web and in web, okay. And the third one is IPB, has this shape too, but in IPB section the length of upper of profile is too high, is too long, I mean the length of flange of IPE is a bit long. This is flange of profile and this is web of profile. In the IPB section, the value, the length or the length of flange is approximately equal to web length or web value, okay. And the fourth steel profile is channel. We all know that with this shape. And we have L section 2, L profile 2 with this shape, and we have T profiles which has actually this shape. Okay, and we have Z profiles which have this shape. This is not exact shape. I just want to show that because I cannot paint them correctly. Okay, and we have these were the most important steel profile that we use them in building. Okay, let's continue our job. Now I want to introduce you with the geometric parameter of steel section in design of steel structures. Okay, let me write the subject, everybody. Our subject is geometric parameter of steel sections. Okay, first of all, I want to introduce area of section that we show that with A, which is area of section. The second one is elastic neutral axis. We will introduce them one by one completely, okay? In this slide, I just want to show them. The second one is elastic neutral elastic neutral axis with that we show that with Y bar elastic is renowned with this letter The third one is plastic neutral axis. Let me write that. The third one is plastic neutral axis, that we show them with bar P, you know. And the fourth thing that we all know familiar with that is moment of inertia. Moment of inertia, that we show them with let me change my marker. Just want to, sorry, I just want to show them with the red pen. The first one is area of section. Okay. That I show them with a letter. I show elastic neutral axis with a Y or E. I show plastic neutral axis with a Y bar P, and we show moment of inertia with a I. Okay, the fifth one is elastic section modulus. Let me write that. The fifth one is elastic section modulus. Okay, that we show that with S. I always forgot to show the name with another pen. Okay, with S. And the sixth one is plastic section modulus. This plastic section modulus is very important, and we use that very much in design of steel structures. You know, I will solve some problem about these things, which is plastic section modulus. I show that with Z. Okay, these were the most important geometric parameters of steel, you know, and I want to introduce them one by one. The section of area, you all know that. I'm not going to introduce that, but I will introduce another thing one by one. I want to introduce elastic neutral axis. Okay. or void E. Suppose that, let me write that. I want to write void bar E. Okay, suppose that we have a section which has two parts. This is the flange and this is the web of this section, and we want to calculate the void bar E for this section. This is a flange and this is web. For calculating the elastic neutral axis, we have to assume a basic axis for calculating this. I want to name it basic axis. Okay, and we assume that the neutral axis is somewhere here. We don't know that, we just assume that it's somewhere here. Is this axis is elastic. Neutral is elastic neutral axis, and the distance between elastic neutral axis to basic axis, we name that void bar E. Okay, and how can we calculate void bar E? Okay, we know that both flange and web of this section have a specific section of area, and that's it. The method of calculation is this. I can write that void bar E is equal to sigma AI, which means section of area of every part, times void bar I. What is void bar I? Be patient, I'm telling you. Divided by sigma of AI, but what is void I? We know the section of area of every part. There is no need to explain that. Okay, but I want to write that what is void bar I? Void bar I is the distance between the center of area of every part to basic axis. Okay, let me write that. Here is the distance between center of area of every part to basic axis. Okay, this is the definition of y bar I. For example, now I want to make a value for this part, okay, and calculate the value of elastic neutral axis. Okay, I want to suppose that the width of flange is 50 millimeter and the length of the flange is 180 millimeter and the length of the web is 200 millimeter and the width of the web is 40 millimeter. Okay, let me to calculate the value of elastic neutral axis for you. Okay, let's calculate. The y bar E is equal to A1, which is flange, times y bar of flange plus the area of web times y bar of web divided by A1 plus A2, the area of flange plus the area of web. Okay, the y bar E is equal to the A1, the area of flange is 180 times 50, you know, times the y bar A is the distance between center of area, which is here in the center of flange. In the center of flange we have 25 meter from here and 25 millimeter from here, and the distance between center of area to basic axis is 200 plus 25, which is 225. Okay, times 225 plus 200 times 40, which is the area of web, times 100. I hope that you understand how do I write 100. Let me change my marker. The center of area of this web is here, you know, and the distance between center of area to basic axis is 100. This is the center of area. Okay, and now you have to divide this value by sum of the area, 180 times 50 plus 200 times 40, and the result I've just calculated. I don't want to calculate that because it's very it has explained many times. Okay, is 166 millimeter from the basic axis, you know, which is somewhere here. Our first atomic word was true, you know. Okay, these were the definition of elastic neutral axis. You know, we have to know these comprehensions for flexural contents. You know, suppose that we have a beam, we have a I beam, you know, I mean our beam profile has INP or IPB, okay? When a fractional moment applies to this section, we have half of section in tension, we have half of section in compression. For this issue, we have to learn the neutral, elastic neutral axis, plastic neutral axis. You know, these were a basic parameter. These are a basic geometric parameter for a steel, you know, and every engineer should know them. For knowing this, I want to draw a I profile for you. As always, I'm not a good drawer. I apologize for that. Okay, this is the I section, and I want to apply a fractional moment on this section. For example, here is our neutral axis in fractional moment, and the direction of our moment is like so. Okay, we know that the half bottom of section is in compression because of this direction of moment. We have here, we have this area under pressure, and we have this area half top of area in tensile case, okay, and we have the half top under tension. Under tension. Okay, this section were under negative fractional moment. We have negative fractional moment for this section. But what happens when the direction of moment be reversed? Okay, let me draw that for you. If we have this section again, this thing that I'm teaching is not dependent to elastic neutral axis. I just want you to know that because of these contents, we have to learn elastic neutral axis, plastic neutral axis, and etc. You know. Okay, this is our section, and we have our neutral axis here, and these were neutral axis too. And the direction of moment now is different. This is our moment direction. Okay, so you all now guess that what is happened in our section. We have the half top of our section in compression. This half top is under compression, and our half bottom of section is under tension, because the direction of moment have been changed, and we have here positive flexural moment. Okay, these were a basic content in our civil engineering, and I want you all to know that. Okay, now I want to introduce you with plastic neutral axis. What is plastic neutral axis? Let me write our topic later. We want to know the plastic neutral axis. We call them Y bar P. Now we want to calculate that. Y bar P or plastic neutral axis. You have to know that plastic neutral axis divided our section into two parts with the equal area of set. Okay, this is the definition of area of plastic. So let me repeat that. Plastic neutral axis divide the section into two parts with equal area. Okay, what does it mean? Let me draw a eye profile for you. This is our eye profile. And the place of plastic neutral axis is where our section have two parts with equal area. For example, our section of area, our plastic neutral axis is here. For example, this is the place of this Y bar P. If here is the place, we have the area of this part, which we call it A top, is equal to this part, which is area of bottom. Okay, we have uh, area of top equal to area of bottom. Okay, so this was the definition. Now I want to solve a problem for you, a real problem for you of solving the plastic neutral axis. Suppose that, let me close this topic. Suppose that we have a I section sorry for bad terrain. Okay, and the flange has a plate 500 times 20 millimeter, and the web has a plate 400 times 10 millimeter, and the bottom flange has a plate 200 times 30 millimeter, and we want to find the place of plastic neutral axis. Okay, we know that the plastic neutral axis divide our section into two parts with equal area. Okay, we have the area of flange which is 10,000, and the area of web is 4,000, and the area of bottom flange is 6,000. Okay, so we have to know that the area of the place of plastic neutral axis is here. We have here the place of neutral axis, because the area of top, let me write that, the area of top is 500 times 20, which is equal to 10,000 square millimeter, and the area of bottom is equal to 400 times 10 plus 200 times 30, which is equal to 10,000 square millimeter. And now the area of bottom is equal to area of top. So we have determined the place of plastic neutral axis. Okay, can you tell me how can we calculate the place of elastic neutral axis in this problem? Let's get started. Let me calculate the place of y bar E in this problem. The value of y bar E is equal to, can you tell me? Okay, we know that y bar E is equal to sigma area of every part times the y bar of every part divided by sigma of area of every part. Okay, now our y bar E according to the careful that we calculate all of these parameters according to basic axis. Okay, let's get started. We have y bar E to be equal to the area of flange, which is the area of bottom flange, which is 200 times 30 times, what is the y bar of bottom flange? As you know, you all know, the y bar is 15 millimeter. The distance between center of area of flange to basic axis is 15 times 15 plus the area of web is, which is 400 times 10 times 230, you know, because the half of web is 200 and the other distance is 30, plus 500 times 20 times 400 plus 30 plus 10. We have the center, and this is 10, plus 500 times 20 times 440. Now we divide all of these values to area of every part, which is 200 times 30, you know, plus 400 times 10 plus 500 times 20, and the answer is 270.5 millimeter. This is the answer. And now can you tell me what is the distance between plastic neutral axis and elastic neutral axis? Let me write that for you from the basic axis. You know, we had the distance of plastic neutral axis to basic axis is 400 plus 30 is 430, yeah, is 430. Let me write that with another mark. We have y bar P is equal to 440 millimeter, and we have the distance of elastic neutral axis. Our elastic neutral axis is somewhere here approximately. We have the distance to basic axis of y bar E is equal to 270 0.5. Okay, now we can calculate the distance between them. The distance between, I want to because of the value of y bar e is less than the value of y bar p, we have to write the absolute value of distance. Okay, the absolute distance between y bar e to y bar p is equal to 250.5 minus 430, which is equal to 159.5 millimeter. Okay, this was the answer of our question. Okay, I think our session become a bit long and you're all tired, and I want you all to not to be tired, and if you feel so, please drink a tea or coffee to continue. In this session, let me remind you what we have taught in this session. At first, in this session, we introduced the tension and strain diagram of steel. You know, we have introduced the yield stress for steel and the ultimate stress for steel, and we told that what is happening in steel diagram under pressure, and we have introduced the engineering properties of steel, like modulus of elasticity, yield stress, and ultimate stress for most common type of steel that we call it S235JR or SD37. Okay, we have continued, and we introduced Poisson ratio, temperature coefficient, and shear modulus of elasticity of steel. We told that what is Poisson coefficient. I told you that because of axial load, we have increase in value or increase in lateral mass of body, and this is the Poisson ratio. I try to, it's actually a very broad topic. I just and I have that plan to make a video for that. Okay, and we have continued, and we have introduced most common type of profile in steel structures, you know, and those were INP, IPE, IPB, channel section, L section, T section, and Z section. You all know that. This is channel section. Okay, and this is L section. Okay, and we have introduced them, and then I have introduced your most important geometric parameter of a steel section. Okay, which were A, Y bar E, Y bar P, moment of inertia, elastic section modulus, plastic section modulus, you know. Let me, and then we have solved some problem for elastic neutral axis and plastic neutral axis. We have illustrated them completely, and then we have introduced the void bar P, which were plastic neutral axis, and I have explained that completely. I have solved the problem, and in the end we have calculated the distance between void bar E and void bar P. That's all, everybody, and I want you all to I hope that you all enjoy this video, and if this video has some problem, and I know that this is not complete, I just want to learn you and teach you, and if I want you all to like it. Actually, if you all like it, please sub the channel, everybody, to motivate me to create more videos for you. Thank you, everybody. Thank you very much.